Hello, and welcome to this webinar presented by the IET Cambridge Network. We represent folks in the Cambridgeshire area, but we're very pleased to welcome everyone from elsewhere, especially this week, which marks the 150th anniversary of the IET. My name is Phil Zangast. I'm the chair of the local network, and I'll be your host tonight. And before we get out of the way, I'll just cover a few housekeeping issues. We will be taking questions tonight, but at the end of the presentation. So if you think of something, please use the Q&A button, which you'll find at the bottom of the screen on the Zoom control panel. We'll try to answer all your questions tonight, but if we don't get to them, we'll record those, and our speakers have offered to answer those offline, and the answers will be posted on our IET Cambridge website. We'll be recording the event tonight, and that'll be available in a little while on our YouTube channel if you search for IET Cambridge. And I'll mention that the IET is running a survey at the moment on diversity and inclusion and how best to represent its members, and I'll post some details in the chat panel during the event tonight. So on to tonight's event. I'm very pleased to welcome our two speakers this evening. We have Dr. Stuart Hilmanson and Ross Loades. Stuart is a reader in railway traction systems at the Birmingham Centre for Railway Research and Education. And over the last decade, he's been working on the potential for hydrogen as a fuel for railway applications. And he's the academic lead for the HydroFLEX project, which is a collaboration between the University of Birmingham and the rail leasing company Poprterbrook. And Ross Loades is a systems engineer at Poprterbrook, and he provides technical support to new on-train systems and supports innovation projects like the HydroFLEX project, which we will hear about tonight. So without further ado, I will hand over to Stuart and to Ross to talk about the HydroFLEX project. Thank you.
Thank you very much, Phil, for that introduction. And I did notice that the participant list just got over 200 while you were doing the introduction, which I think is one of the biggest audience we've had the opportunity to talk to about our HydroFLEX project. So it's an absolute pleasure to be here to tell you the story of HydroFLEX. And myself and Ross are obviously really keen to get feedback and from you. So if you post stuff in the question and answer session, we'll try and address things as things pop up, and also at the end of the session as well. Ross and I are doing a joint presentation, and he'll be driving the slide, so I'll be saying next slide, but I don't mean that yet, Ross. Okay. Then I'll hand over to him, and he can just drive them from then on. So you're looking at a picture there of the HydroFLEX train as we ran it on the main line in September last year. Seems quite a while ago then. HydroFLEX is pretty much the only train I've been on in the last year, actually, as well, which is, I think, an interesting thing to put on my CV, that I've only travelled on hydrogen trains for over the last year. But that's more to do with the pandemic. This is pretty an iconic picture, I think, because it shows a picture of an electric train travelling on a non-electrified network. And that could have real significance for railways going forward in the future. Obviously, electrification is massively important to the industry, and Poprterbrook, our partners in this, have got lots of electric trains, and indeed that's the best way of running really high performance, high density, high power, high speed services. So all the things going in and out of London and the major cities have definitely got to be electrified. But well over half of our network isn't electrified, and we need to solve the problem of how do we power those trains in a decarbonised way in the future, and also in a way that doesn't pollute the air that the people around the trains are breathing in as well. And we think that hydrogen has got a real good potential to tackle this problem. So next slide, please, Ross.
There we go.
Thank you. So what's it all about? So at Innotrans 2018, we formed a partnership with Poprterbrook and linked through our University Activity UK Railway Research Innovation Network. We came together in a collaboration which would then convert one of their Class 319s into a hydrogen train. And this was a match made in heaven, really, because Poprterbrook had already done a huge amount of work on re-engineering Class 319s into diesel flex trains. So they had the understanding about how to take an existing electric multiple unit and turn it into an autonomous train with its own onboard power supply. So there's a great deal of understanding on how to do that. And then the team at the university had expertise in fuel cells and hydrogen storage, and we combined that together, and then we're able to develop a prototype in 2019, which was just a 9-month project. Next slide, please. So this is a rough overview. So I'll be telling you why we're doing this and introduce HydroFLEX, and then sort of halfway through, then I'll hand over to Ross, who'll talk a little bit in more detail about the ins and outs of the train and mainline testing, and also where we're looking forward to in the future. So next slide, please. And the next one. So what the reasons why we're doing this, and most of you hopefully will be aware of these things, the key challenge is all diesel trains need to be scrapped by 2040, which in railway terms isn't very long at all. You know, that's 19 years away. Indeed, if you have a train that's 19 years old, that's actually a very young train in the fleet, to be honest. So you can't really buy a diesel train now, because you're going to need to retire it by 2040, which wouldn't be acceptable, and you wouldn't probably get enough income over the life of the train to justify buying it. So it basically means we're not able to get new diesel trains onto the network at the moment. So we need to start looking immediately for it. So there's two challenges. One is decarbonisation, and also cleaning up air quality. So obviously diesels produce particulates and NOx and other nasties, and these are becoming increasingly unacceptable, particularly in city centres. Next slide, please. One of the key factors affecting us, whether we can use hydrogen or not, is also how our energy generation mix is changing in the UK. So you hear in the news often the fact that our mix of power generation is increasingly becoming renewable. We're forever hitting records of the amount of renewables that are being fed into the grid, and this is going to continue, and by 2050 the grid should be zero carbon. So it doesn't really matter how much electricity used, because it will then have no impact on carbon dioxide emissions, and therefore, you know, we can use as much of it as we like to some extent. It just becomes an economic commodity, doesn't have an impact on the environment, which will be a great place to be. Next slide, please. Hydrogen is already a mass-produced gas. There's huge quantities of it produced globally. Most hydrogen is used pretty much immediately to make things like methane, which then go into other chemical processes. So you use hydrogen to make nitrogen-based products, which are used for fertilizers and things like that. So there is already a hydrogen industry in the UK, but most people aren't aware of it. And there's also hydrogen used for transport, and you may know about the Tees Valley project. So there's a huge investment going into Tees Valley to produce a hydrogen hub. With lots of demonstrator and prototype vehicles going to be running out of there. And then other places also dip the toe in the water in terms of running hydrogen vehicles. Next slide, please. And here are some of the example types of vehicles that are in service. So there's been buses running in Aberdeen for a number of years now, also London buses and things like dust carts and so on. So you know, these are kind of ideal examples of applications of fuel cells, because you have a vehicle which is heavily utilized and returns to a base station each night, can get refueled for the next day's operation. So we're very much taking technology of this scale and then translating it into rail applications. So we're borrowing from the bus sector and automotive sector and translating it into railways. Next slide, please. At the university, before we developed the partnership with Poprterbrook, we realised that this challenge was coming, and we thought that hydrogen fuel could be used as a fuel for railways. And we started doing concept design work and early sort of calculations of what exactly could hydrogen do for railways. And we've done lots of paper-based exercises, and that's led to small-scale demonstrators and then the HydroFLEX project eventually. An important thing to realize is hydrogen is an energy vector. So, it doesn't exist. We can't dig it out of the ground. It doesn't exist on its own. So we have to make it, or we make it from a feedstock such as methane. So if you do that, then it does have a carbon dioxide penalty, and you might want to bury that carbon dioxide or release it to the air, and that'll have very different impact on how green hydrogen is. But ultimately, you can produce hydrogen from electricity, and if that electricity is zero carbon, then you haven't used any carbon in the production of a fuel which can be used for mobile applications. However, if you're using electricity to make hydrogen, then putting it through a fuel cell to make electricity again, you throw away about 2/3 of the electricity or thereabouts, which means that you're wasting a lot of electricity. So this is a good point, and people say, why don't we just electrify everything? But then that goes back to the picture I showed you at the beginning of the presentation. Many of our lines are in quite rural places where you only have a small number of trains per day. And it just wouldn't be economic to get to recover the cost of electrification in the really rural parts of our railway. There just simply aren't enough people travelling on it to justify the huge costs of electrification. That's not the case if you've got a very busy railway, of course, and high performance one. Electrification is the answer there. So we're looking for answers on railways which are quite rural and remote, but equally they're very important parts of the railway. So next slide, please. And the next one. So got some pictures now of HydroFLEX. I'm just going to give you an overview of the main bits and pieces that we have in HydroFLEX, and then hand over to Ross shortly. So there's some pictures of what the train looks like on the outside, and obviously this is a Poprterbrook train, and they made it look beautiful on the outside. Me as an engineer and Ross, I think Ross probably goes for Ross as well. We were very interested in the propulsion system and the electronics and the control, and other people within Poprterbrook very cared a lot about how it looked as well. But we were very excited about how it worked. Next slide, please. So the vehicle that we converted was class 319. It was actually 001, so the first in the series of that, and it'd already done a lot of work and done 2.5 million miles in its life, and then with us eventually it did 75 miles on the main line and hydrogen power, which is probably the most significant mileage it's done in its life. So it's an electric train, which is 25 kV overhead supply, but also can take power from the third rail. So crucially, on board the vehicle is effectively a voltage bus, which then is fed into traction motors via chopper controlled converters. So that DC bus, when the train's used on the railway, that bus can vary quite a lot. So it can go down to something like 450 volts and up to about 900 volts. And we picked a voltage to run it at 625 volts DC. So we basically we got a fuel cell plus a battery system, made it up to 625 volts, or it was actually nearer 650 volts in the end, and then fed that into the traction system. So it sounds quite easy, and it sort of was quite easy on a concept level, but there's a huge amount of detail and nitty gritty that's involved in getting it actually working. So next slide, please. We had to do this really quickly. We decided to put the equipment inside the vehicle because this was a prototype. We didn't want to have the headache of engineering all of the components to go underneath a vehicle, which would be the preferred solution for a vehicle in service. So what we did was take out the seats from this vehicle, the MSO, which is the motor standard only. So this vehicle carries the traction motors on board and all of the converter equipment used to power the traction motors. We took all the seats out of that and installed the fuel cell, the battery, the hydrogen storage tanks and the control system, and had some space for Ross and I and a few other colleagues to sit and monitor everything. So there are two reasons. One, this was a lot quicker to do the engineering this way, but crucially, I think the main reason or the main benefit of doing this was we were able to show lots of people inside the vehicle and give them a tour of the vehicle, show them around, and allow them to poke things. Obviously there was no exposed high voltage stuff anywhere, and that was very, very powerful in terms of allowing people to see what the fuel cell looked like and what the storage tanks looked like, and so on and so forth. So that was a major achievement in disseminating and demystifying a lot of the things about hydrogen tanks and so on. So several thousand people, I think, have probably been in the vehicle to have a look at it, and probably several thousand have actually had trips on it as well, because we ran it in Long Marston for a number of different events, and it got a lot of interest, including we've a trip with the Secretary of State of Transport, Grant Shapps, riding on it when we took it on the main line. Next slide, please. So these are some pictures of the inside. So we took out all the seats, and you can see some tapping blocks fitted in the floor. So these are attached to really strong parts of the train, which are basically used to mount the seat railings. So we mounted all our equipment on existing mounting plates, and there was some strengthening work that we needed to do, and all this work was done to various railway group standards. So although the HydroFLEX vehicle only did 75 miles, it had a fatigue life, for example, of 25 years, and would survive all of the various extreme loading cases that you might have on a rail vehicle. So next slide, please. So here's a picture of some of the equipment inside. So these are our hydrogen storage tanks. So we had 4 tanks on board. Each of them weigh about 100 kilos and store about 5 kilograms of hydrogen. And they're pretty long, and they occupy quite a large volume. 5 kilograms of hydrogen does store a huge amount of energy, and it's much better than you'd ever get out of a lithium-ion battery. So that's one of the reasons we're using hydrogen in the first place. However, the volume of the tanks and the mass of the whole system is much greater than what you'd get for diesel. And that's one of the challenges about a hydrogen vehicle, is you can't go head to head with a diesel vehicle and get the same performance in terms of power or range out of a vehicle that's running off hydrogen. So we need to be more clever about how we're going to use it, and perhaps as this vehicle is fitted with a pantograph, it's possible to use the pantograph on the electrified network and then use the hydrogen fuel cell to run off of the end of the wires when you haven't got the overhead there. So these are tanks, and it says they're designed to EC 79. This is a standard taken from the bus sector. And right now there's an IEC committee working on standards for railway applications for fuel cells and hydrogen storage systems. And I'm actually sitting on that panel for the vehicle system part of it. So stuff is moving rapidly now to make this commercially viable and be able to be deployed on a wide scale. So next slide, please. This is a fuel cell, and fortunately it's box shaped because we draw it as a box in all our system diagrams. It is 100 kilowatts, so it's well below the power of the train. We take hydrogen from the storage tanks, which are 350 bar, reduce it down to something much lower, like around about 8 to 10 bar, and feed it into the fuel cell. So when we used to bring people on board the train, we would point at the hydrogen connection into the fuel cell and say, look, hydrogen goes in there, and then there's 2 cables coming out of the back of it, which are DC power that comes out of it, and that then gets converted through a DC to DC converter and fed into the train. So it's very simple from a functional point of view: hydrogen in and DC electricity out of it. It also needs cooling equipment. So the fuel cell is about 100% it's about 100% efficient. I wish it was. It's about 50% efficient. So 100 kilowatts of electricity that we get out of it, if we were running it at 100 kilowatts, which we didn't always do, we would need to get rid of 100 kilowatts of heat. And in the background, you should be able to see some cooling fans there. So we have a radiator with deionized water that flows through the fuel cell and cools it. We spec the radiator to deal with like ambient conditions of about 40 degrees, and we would have been able to run the fuel cell at full power with air at 40 degrees. It is a challenge cooling fuel cells actually. But something that we've developed expertise in. The fuel cell was controlled with CAN bus and some hardware signals, and researchers at the university developed the hardware and software to control the fuel cell and integrate it into the train system and make sure that all worked really well. So next slide, please. The fuel cell didn't work on its own. We also have a lithium-ion battery pack. It's actually 2 batteries effectively, with 12 modules in series to form a battery, which had a roughly voltage of 625, and then those 12 modules are paralleled up. So we have 24 modules in total that fed into the train traction bus. I think the thing to remember is that the battery was much more complicated than the fuel cell. To be honest, there's far more components in the battery, and there's a huge amount of inbuilt protection in a battery system such as this. And we had to do quite a lot of work in terms of making sure that the battery was happy in a railway environment, because initially it wasn't. A railway traction environment is very, very aggressive. There's quite a lot of electromagnetic noise about as well, and you know, this battery is trying to look after itself, and we needed to make sure it was robust enough to work in the rail environment. And so it caused us probably quite a lot of issues integrating it into the train system, which we overcome in the end. So next slide, please. So how's a fuel cell work? This is, probably should have said this right at the beginning. Fuel cell works by pushing hydrogen into into the fuel cell as a gas. Then there's a catalyst, an anode catalyst, and an electrolyte and a cathode catalyst. Air is pushed into the other side of it, and then the hydrogen lands on the catalyst and does something magic and turns into protons and electrons, and the protons then go through the membrane. So it's called the proton exchange membrane. Protons go through it, go to the other side, because they're attracted by the oxygen ions over there, and they join together with the oxygen ions and form water. So we get a waste product of water, and the electrons have to go around the other side to complete the chemical reaction, and they travel through an electric circuit in order to meet the hydrogen ions and oxygen ions on the other end and form the water. So we can drive an electric circuit using this process. So fundamentally, it's more like a battery than a combustion process, and therefore can have much higher efficiency than a combustion process. So that's why we don't burn the hydrogen in a combustion engine, because a fuel cell generally can produce higher efficiency than combustion process. So next slide, please. We also needed to refuel the train, and this is quite a challenge because you can't really, you know, we had to do a lot of work in this area. There's no real off-the-shelf system ready, so we developed something with a company called Fuel Cell Systems, and the red tanks that you can see there are the hydrogen which we obtain from BOC, and we take hydrogen out of there, pump it up to higher pressure, and inside that van are some high pressure cylinders, so we can go up to well over 500 bar, and then we can discharge that or decant that into the train rapidly and fill the train up in 10 to 15 minutes. So the principle is you take low pressure hydrogen, pump it up to very, very high pressure, and then you can decant it into the train rapidly for refueling. So next slide, please. And this is the end of my bit. I'm going to hand over to you, Ross, and sit back and relax and enjoy your part. So, thank you, Ross.
Thanks very much, Stuart. I might cover some of the stuff that Stuart's already said, so I do apologise for that. So yeah, the hydrogen fuel cell and the battery that Stuart's just gone over connects together in a T arrangement, with the bottom of the T going down to the traction system on the train. So that runs through the unit's AC bridge rectifier, and then through the GTO choppers, and then to the traction motors. Now, aside from this rectifier, it's a very similar arrangement to most hybrid cars, where the internal combustion engine and the battery work together to power the drivetrain. So I mentioned the rectifier. There was a reason we went through the rectifier, even though we were running DC. The AC side of the 319 traction system actually has a pre-charge circuit, which helped us to reduce any initial current spikes. Okay, so the Class 319 units are nominally 1.2 megawatts on AC or DC from the OLE or the third rail, and the traction control system is known to be quite aggressive. It does incorporate some closed loop control, as you can see on the screen, but it's quite basic, and if left standard, would easily overwhelm the battery and the fuel cell together, which would shut themselves off to protect themselves. Fortunately, as Stuart has alluded to on one of his opening slides, we have the Flex project between Poprterbrook and Brush Traction. So they use 2 diesel engines under each end of the train, and the 2 engines add up to a total of 780 kilowatts. So they needed to sort of control the power that the train was demanding to fit into the use profile of the engines. That's where we adopted that technology from. So the Flex project uses an enhanced current monitoring device, or CMD, which inserts an additional gain into the feedback loop here. So this essentially fools the train's traction computer into thinking that it has the power that it's expecting, when in reality it doesn't, which allowed us to power a 1.2 megawatt train with just about 200 kilowatts. So that's how we did that. So initially on the day, this was manually controlled. My colleague Ralph was sat at the laptop, looking at the current, and then turning the gain up accordingly. So that's the CMD box on the left there, and the potentiometer on the middle there is the gain control. And there is my colleagues Jeff in the baseball hat and Ralph opposite, Ralph controlling the CMD and Jeff monitoring the fuel cell output. So for phase 1, the manual gain control was fine, but the CMD system also has the ability to automatically control the gain to a set power level, and that's a feature that will become useful much later. So so we built the train, as Stuart said, in 9 months. We had a few weeks to test at Long Marston, and then it was time to show the train off at Rail Live. We successfully carried a lot of visitors on the train. We did short shuttles around the Long Marston site, and even had some early morning news footage on the Good Morning Breakfast on the BBC. Rail Live testing done. It's now onto the bigger picture, which is mainline testing. So the initial conversion was only intended to run at Rail Live. So we then had a lot of work to do to get the train ready physically, and with lots of paperwork to run on the mainline network. Most of this second stage was funded by Innovate UK, which also had a target of Q2 in 2020. So yeah, we had some improvement work to do to the train and lots of paperwork to catch up on. That was the Q2 was the plan, but then this big pandemic hit, so that kind of affected things a little bit. So with COVID happening, we still progressed with the project, and we designed and developed the improvements to the unit, which included automation of the power control for both the fuel cell and the current monitoring device. We had some physical rework to do on the train, and then a completely new logic unit to be inserted in between the driver's power handle and the traction controller. So this is the new logic box that was designed. The first thing I want to point out here, before I go too much into what the logic box does, is that the principle of these were to not create any false signals on the driver's inputs, so that we couldn't control the train, we were just interrupting what the driver was doing. So the new box essentially added a delay between what the driver was asking for and what the train was able to get. So this gave the fuel cell a bit of time to ramp up to the demand required, and it also changed the power level on the current monitoring device so that we had the right power level set depending on what power sources were connected. The last thing in the box was some wheel spin control. Now this was done by backing off a notch on the power handle when wheel spin was encountered, and then if further wheel slip was encountered, it back off again. So we successfully undertook all of our modifications, and we also got a lot of paperwork done, so much paperwork. So we had 175 hazards generated and closed out individually. There were 177 different pieces of evidence to go with those hazards, and then 102 technical integration drawings to show that this was designed and engineered properly. There were also 2 hazard identification sessions with everybody invested in running the train involved, which generated the hazards. We also had a statement of compatibility to raise, which raised 69 technical questions, which were individually responded to. There were 10 comments on the statement of compatibility, and Poprterbrook has an internal engineering change control process that had to be gone through as well. But arguably the biggest bit about proving that a hydrogen train is safe to be on the network is the fact that it's the first one. There are no, as Stuart alluded to, there are no standards to govern hydrogen trains on the railway, so we had to adopt EC 79, as Stuart said. The other thing, which you wouldn't really think about, is the perception of risk. If I talk to people about working on a hydrogen train, some of them make a comment about, oh, Hindenburg and hydrogen is unsafe, which totally isn't the case at all. We've gone through a lot of robust engineering and a lot of detailed thought on hydrogen to make it safe, and that's what the standards are there to do as well. Lastly, the role of integrator is something totally new to a leasing company such as Poprterbrook. Traditionally, we'd go to your Alstoms or your Siemens of the world, and we'd get them to do the project and we'd pay for it. This is a new role for us. We're not usually the project integrator, so it's breaking new ground for us as well. So part of the compatibility work was to get the train EMC tested, which you can see on the left with some of the antennas they pull out to test the signature of the train. And there's my 2 colleagues, Ralph and Jeff, again on the right. So this is used to test the compatibility with the network for signaling, for the safety systems like AWS and TPWS, and to check that it's safe for people to actually be inside the train. So the next slide is a short video that I'll play, and then I'll carry on again.
So HydroFLEX is the UK's first hydrogen train. It's also the world's first bimode electric hydrogen train, and today has been a historic day because it's been the first day we have seen a hydrogen train running on the UK mainline railway, as we left here at Longmarston and went up to Evesham and back successfully.
It takes a lot of work to get a hydrogen train to run on the main line. There's a huge amount of safety approvals work that we have to go through. We had to formally document a lot of things, record things, assess the hazards, assess the risks.
Hydrogen is really important in terms of being able to offer decarbonisation solutions to the rail industry, mainly because you can produce hydrogen from renewable sources by electrolysing water. And hydrogen is going to be used on the parts of the railway which are just not economic to electrify.
I can't describe how proud I am of the whole HydroFLEX team to get the first UK mainline hydrogen train working. It's been absolutely fantastic project, and it's a personal highlight for me as a career, and also it's a real big step forward for the UK and decarbonisation of the railway.
One of the best things about being at the University of Birmingham is we do really, really good practical and industrially focused research, and we've always had a record of doing that. And we developed this partnership with Poprterbrook just over 2 years ago, and Poprterbrook, from my point of view, have been a really innovative company and willing to take a risk on the technology and working in partnership with us to get to where we are today with the HydroFLEX train.
It's been so exciting for the team to draw together all that work that we've put in and to see it running at high speed on the network, and more importantly to the industry to demonstrate this technology is the future.
So we'll spend some time saving the moment of the UK's first hydrogen train on the network. So on the left there, you can see a picture of the speedometer in the rear cab approaching 50 miles an hour, which we didn't think was possible with only 200 kilowatts on the train. On the right there, you can see that's from the front cab this time, and that's us passing an IEP unit, one of the Hitachi units, between Honeybourne and Evesham. And here's our quick stop at Evesham. So first time we stopped in Evesham, we weren't able to get off the train. This was the second trip we made, and we were able to get off the train and take some pictures. And here's a picture of the train returning back through Evesham. So we went up there, stopped, turned around and came back again. On the first run, we also had to recess into some sidings at Honeybourne. So that's us next to our rescue locomotive, which thankfully was not required. It was a very busy day on the branch, so yeah, they made us wait to get back in. And here's a data logger trace of that run. So you can see us there. We've got to 50 miles an hour. The logger trace says 49, but we know that there was a slight issue with the WSP input on that car. We know it's under reading by 1 or 2 miles an hour. So a project like this, you couldn't do it without true collaboration. We had lots of collaboration on this project with all the collaborators, most of the collaborators there on the left, and a very happy team. Most of the collaborators there on the right, and a very happy team on the left. So looking to the future. So we've done HydroFLEX 1, we've tested it on the main line as HydroFLEX 1.1, and now we're looking to HydroFLEX 2. So the next HydroFLEX is currently in development. We've secured more Innovate UK funding, and we're developing the production version, which now we're in development with the supply chain. It will retain its bi-mode functionality as being able to be powered from the overhead and from hydrogen. We're aiming to get 90 miles an hour out of it in hydrogen. And we're aiming to be competitive with some diesel trains in terms of range. More of the equipment will be fitted underneath the train, but some will end up being in the first driving vehicle. That configuration kind of depends on the range you're going for. It will further be based on the flex concepts used on the Class 769 vehicles that have just started running at Northern and at Great Western, and in Wales with TfW. And we want to build on the project and really learn from it. So we can build these trains and then we can learn for new train projects in the future. And it also opens up the industry to working with new partners on the route to getting hydrogen approved for passenger use. So takeaways from this, infrastructure is quite challenging. It wasn't something that Poprterbrook had expected. And onboard hydrogen storage volume is again quite challenging. It's the size of the tanks, really, the picture really doesn't do it justice. You need quite a lot of room just to store what seems like a small amount of hydrogen. Safety and approvals is a lot of work, but like I said, the perception of risk is more so. You need to persuade people that it's safe, and that was half of the reason of putting the equipment inside. It's about a messaging piece that, you know, you can demystify hydrogen beyond the Hindenburg sort of thing. And the project for many people was a career highlight, mine included. I'm quite fresh to the rail industry. I've been in nearly 4 years now, and it's the highest point of my career so far. And with that, I'm going to finish. Thank you very much.
Okay, thank you, Ross, and thank you, Stuart. We've got quite a lot of questions to go through on the various different subjects, so I will hand over to David Blake, who will take you through those questions. Thank you.
Well, thank you very much, Phil, and thank you very much for the team for giving us an insightful input to the issue of hydrogen trains. I must admit I have a particular interest myself, because I'm still very keen to understand what the proposal will be for the east-west trains going from Oxford to Cambridge, which is very urgent subject in the sort of Cambridge area. Anyway, thank you very much. What we'll do is start with the Q&A. There are quite a few, and I'll basically start from the top and sort of go down. I think that's probably the best way of handling this. First question is, hi Stuart and Ross, good to hear from you. The UK needs to decarbonise home heating. I read a figure recently that the UK would only be able to source hydrogen for 11% of home heating. with such competition for hydrogen, will there be enough for rail, and how will that affect the cost? I'm not sure who's going to answer, so I'll ask the questions. And
yeah, I'll have a go at answering that. I think that's a really important point. I mean, rail has to decarbonise, but as a total contribution to UK decarbonisation, it is really a drop in the ocean. I mean, we use less than 1% of electricity, and less than 1% of the diesel is used by rail. So the real challenge for UK as a whole is to decarbonise the big sectors as well. If hydrogen is used on a mass scale to decarbonise heating, then we'll only need to siphon off a really small proportion of it to run railways. It won't be a massive problem for that, but it's an interesting point. I often think if you actually switched off all the railways overnight and didn't run anymore, you'd barely notice in electricity consumption or diesel consumption for the UK. It's really quite a small part. Having said that, it moves well. It did move a lot of people around pre-coronavirus, and I'm sure it will once we've recovered. So it moves people and goods around the country hugely efficiently already.
Yes, thank you very much. Second question is, I understand the Heritage Railway at Bowness near Edinburgh is also carrying out research into hydrogen-powered trains. Do you have any tie-ins with them?
We know about them. I don't know if Ross, you want to maybe say, I think that the industry is working together on there's a number of projects on hydrogen, and I think we're all keen to know. Well, we're competitive with each other to some extent, but equally we want to be able to present a common message about where hydrogen can be applied. And I certainly know that Ross colleagues at Poprterbrook, and maybe Ross himself, will have had conversations with those up in Scotland developing that project as well. So we're friendly with each other, but equally quite competitive as well.
Oh, understandable.
Yeah, that about hits it on the head, Stuart, really. Competitive, but we're there to kind of share information and share messaging. So yeah, that's where that is.
Okay, there's quite a few questions about the actual hydrogen, and particularly I seem to focus on how green is the hydrogen used in HydroFLEX, as most hydrogen fuels really come from sort of via fossil fuels. And so really, how green is it, and what's the proportion of green and blue hydrogen used by the trains?
So all of the hydrogen that we'll have used on HydroFLEX comes from BOC. We're not 100% sure how they produce it. They have got some electrolyzer capability, I think, but probably the majority of it will come from steam methane reforming. So it will produce that process will produce high quality hydrogen, which is suitable for fuel cell use. It also produces carbon dioxide, which probably isn't immediately thrown away. So carbon dioxide in its own right is a useful gas for many industries. Carbon dioxide is used for many industries like food industries and so on. So, but ultimately that will get emitted to the atmosphere. So there is a carbon dioxide footprint associated with HydroFLEX at the moment, but ultimately you can produce hydrogen from electrolysis of water and renewable electricity, which would have zero carbon impact.
Okay, have you looked at ammonia rather than H2 hydrogen?
I mean, not in detail. I think that question has come up before, and lots. The ammonia is quite a good way of actually storing hydrogen per unit volume and per mass. So you can have processes which take ammonia and then convert it on board, if you like, to hydrogen to be used in a fuel cell. But we haven't gone into detail that. I think those technologies are at a lower maturity level, whereas we were able to go and buy a fuel cell and tanks and all of the equipment pretty much off the shelf and put it on a train within 9 months. Ammonia isn't there, but I would say probably, maybe I'm speaking for Ross now, but they're agnostic about this stuff. If a ammonia system came along and it worked, they'd have it on a train. So
yeah, pretty much, Stuart. Yeah. Doesn't matter what it is, as long as it works and it's reliable. Yeah.
Okay. There's a question about the routes. Are you looking at long distance rural routes, you know, from the far north line, for example, in Scotland? And if so, would you consider hydrogen stops along the side of the track, similar to water stops used for steam trains?
That's a good question. I think we're aiming to cover pretty much an average diesel train diagram. So I can't remember figures off the top of my head, but we're looking at a situation where you'd fill up hydrogen, fill up the train at night, and use the train during the day, and then fill it up at night again.
Okay, okay. So we can't look back to the days of steam where they even had collectors under the track, if I remember. I can't imagine how you'll do that with hydrogen, but there we are. Why not battery electric trains with rapid charging either where the rail network is electrified or at stations?
I don't think it's why not. Well, the way we see it is there's going to be a mix of propulsion in the future. So you'll have pure electric trains which run 100% of the time on the mainline network, and then I suspect there will be electric and battery trains. And batteries are pretty much only good for running a train for about an hour or so. Nobody's got a battery that will last as long as a hydrogen system will. So if you've got gaps of say around 50 to 80 kilometers, you can probably do that on a battery train. And actually in Germany, this is a real contender actually for linking up the electrified networks in somewhere like Germany. But the UK is a bit different, where we've actually got electrification kind of emanating out of London, and then quite long lengths of it in long lengths of non-electrified line outside of London. So batteries won't do the extremities of the network because it's just simply too great a distance. But there could well be a mix in the future of pure electric, battery electric, and then battery, fuel cell, and bi-mode. So a mixture of all three, really.
Okay. There's several questions, in fact, about the costs of overhead electrification, hydrogen fuel, and also battery electric. And really, I think people are trying to get a feel as to the capacity of a fuel cell against sort of batteries. Is it purely the storage capacity of the batteries?
Yeah, shall I have a go? I mean, the economics one first. I mean, we at the university, we believe that electrification is a really sensible way of running railways, but we just simply don't have time or the money to electrify the network as quickly as we need to. So we need to kind of tackle the problem from both directions with electrification and autonomous decarbonized vehicles going head to head, and eventually we'll meet in the middle, and all the diesel will be removed. But we're hoping to be able to electrify continuously in the future, and there's been a recent push to get the government to try and buy into a whole scale long-term electrification program, which I think everyone would support. But whether we end up with that, I don't know. But the railway can't hang about and hope we get electrification. We need to come up with a solution that will solve the problem anyway. In terms of hydrogen does store an awful lot of energy per kilogram, but we need those big voluminous tanks to store it. So a hydrogen system will always be a battery, and if you want to extend the range of a hydrogen system, you just add more tanks. You don't need to buy another fuel cell, as it were. Okay. So the range of a hydrogen system is much more. Indeed, the Alstom Island, I think, has something like 1,000 kilometer range. So it can do a whole day's duty cycle with one fill-in per day. Batteries at the moment just wouldn't be able to do that. You could build a battery train and it'll run for an hour and a half or something, or 2 hours at the most, and then need recharging, which might work, but it won't work on the routes that we're looking at.
Okay. On the first HydroFLEX slide, it says that this was the first full-size hydrogen train. The question is, are there any smaller examples?
Yeah. Sorry, I'll answer that again. The University of Birmingham developed a little fifth scale train.
Okay.
That was run as part of. I hope I'm allowed to say the Institute of Mechanical Engineers Railway Challenge.
Oh, that's okay.
So they run a challenge, and we students from the university and researchers built a 1 kilowatt locomotive that was the first one that ran in the UK, and that was, I think, in 2012 that we ran that, and
Okay.
and that got a lot of interest actually, and got people thinking about the application of hydrogen on a bigger scale.
Okay. Somebody's keen on HSTs and the fact that it's got a couple of diesel electric motor cars. In theory, could they be removed? The diesel generators removed and put a fuel cell and battery in there?
In theory,
train, I would think.
In theory, you could. It's the fuel cell and battery themselves wouldn't be the issue. It's more the storage of hydrogen to take that to undertake the range that a HST would. In theory, it's possible. It's just storage.
Yeah. Okay. How can we produce doghouse hydrogen for transport and possibly home heating? I'm not sure personally what doghouse hydrogen is, so maybe you know.
No, I don't know. I don't know either. I saw that question. I was wondering what doghouse was.
No, well, okay. Perhaps somebody will come up with the response. Yeah. Do the tanks fit under the floor? Can't put them on the roof as on the continent, obviously because of tunnels, etc. Or do we need a separate vehicle like the one with the diesel engines in the stator? That's the Swiss bi-modes.
I don't know if you want to take that one, Stuart, or do you want me to take it?
You go with that one.
Okay. Yeah. So we could fit hydrogen under the floor. As you've heard from lots of sources previously, the British loading gauge is quite small, as you've alluded to, as you've said, on the continent for hydrogen fuel storage on the roof. So we could fit some under the floor, though the range would be fairly limited. So a better solution would be to have a vehicle like the Stadler bi-modes.
Okay. There is a company at Long Marston converting redundant tube trains into quality battery trains for Welsh rural lines up to 60 miles. Battery gives 100 miles. This seems to compete with much superior efficiency. I don't think that's quite what you've been saying, is it?
Well, I think the efficiency point might be in terms of the charging of the battery is more efficient than producing hydrogen from electrolysis and then making electricity again. So from that point of view, it is more efficient on a kilowatt hour to kilowatt hour point of view. But I think the challenge there is the performance of those trains is designed for short routes and not very long. Whereas the kind of vehicles that Ross wants to lease out to their customers need to go faster and further, and at the minute we can't do that with a battery. Okay,
perhaps you may know the answer to this. Is it a challenge to undergo CSM-RA assessment and interoperability approvals?
Yes.
You said that would come some conviction, so you obviously got. Yeah. Okay. Two basic questions.
I would say, I mean, Poprterbrook led all that stuff, and it's kind of we say it's hard, but actually Poprterbrook are experts at it and made it easy and went through it in a very professional way. To be fair.
Okay. Do you use regenerative braking?
Not on the 319, but we could do if a fleet was fitted.
Okay. The work looked at the total system economics from the capital costs of the train and system through the electricity used to make H2 to what eventually gets the useful output of the rail OPEX. Can H2 economics justify branch line operations?
I think the answer is yes. So the way the cost of running a hydrogen train right now is going to be more than a diesel train on a non-electrified route. So it will be more expensive. But what we should be comparing it with is the cost of electrifying a rural route and how that only had like 4 or 5 services a day on it, if you wanted to recover the cost of that electrification, it'd be really difficult to do it through the fare box, and it'd have to come from another part of the railway to do it. All of the calculations that we've looked at suggest that you could, even though the hydrogen is going to be more expensive per kilowatt hour you get out of it, it should be economic to run the train. And after all, you know, we will be able to recover that cost through the fare box.
Okay. There's a couple of questions which relate to one another. How far would the train travel on a full tank of hydrogen? And do you have to dedicate an entire coach realistically to the batteries and hydrogen tanks for a final model? I presume this depends on the size of tank that you're using.
Yeah. Do you want to go for that, Ross?
Yeah. So for the first question, how far the train would travel, HydroFLEX 1, we estimate about a 50-mile range, wasn't it, Stuart?
Yeah, 50 to 75. It depends on how you drive it, to be honest. So
yeah.
If you stop a lot and things and hang around, then no. But yeah, we comfortably did a 25-mile round trip, and I think one time we used 7 kilograms of hydrogen for that, but we depleted the battery a bit. So yeah, yeah, we'd easily get 50 miles, if we pushed it, maybe something like 75 miles. But this was just a prototype after all. We weren't trying to make a full-scale vehicle, which was what we're engaged in now. And maybe Ross, you can pick that up in terms of the full-scale trial.
Yeah. So for the second question of having to dedicate an entire coach, it does depend on the tanks used and the range that an operator would want to use with the train for.
Okay. And then we've got a couple of questions which relate again to one another. Basically, what's going on in other countries? And are other countries developing hydrogen-fueled trains?
They are. Company Alstom have developed a hydrogen train that has been running quite successfully on the continent. And I believe they've just had an order as well for more.
Okay. Right.
And there's a number of there's a lot of interest on this around the world, actually. So many railways aren't electrified, and many countries around the world are also trying to decarbonize. So the problem we're facing is not unique. And interestingly, even in places like North America, there's interest in decarbonising some of those locomotives they use for heavy haul, which could be done with hydrogen in certain circumstances. So yeah, there's a huge amount of interest in this around the world now.
Okay. Are you able to say what the HydroFLEX 1 budget was?
I'm afraid not.
That's okay. I didn't think you'd probably want to, because obviously you've got competitors listening into this one, we think. With regards to potential trial routes for commercial operation, are places like Windermere to Oxenholme in the Lake District, York to Leeds via Harrogate, and Manchester, Piccadilly to Chester, are they the sort of things that you might consider to be used?
I think we'd consider wherever a TOC would be happy to use the train.
Okay. And there's an interesting technical one here. What practical issues are there for a 200 kilowatt train as opposed to a 1,000 kilowatt train? And what power levels are you aiming for on HydroFLEX 2? So
HydroFLEX 2 will aim to match our Flex product. So that's about 800 kilowatts there or thereabouts. That's what we're aiming for HydroFLEX 2. And the practical issues for running a 200 kilowatt train as opposed to a 1,000 kilowatt train. It's it's a lot. The train is expecting it's 1,000 kilowatts, and it's quite aggressive with asking for it, quite frankly. So being more even aggressive to asking for 200 kilowatts does kind of overwhelm the battery and the fuel cell. So yeah, we had to. That was the objective of the CMD, to sort of fuel the train into thinking it was getting what it wants, and then making sure that we could adequately run within the power bounds that we had.
I think just a comment from me on that. You know, I'm academic and I like these sort of things, but the train's 140 tons, and we were running it at 50 miles an hour with half the power of a Tesla, basically. So it just shows you how good a train is at moving stuff around. That just half a Tesla could run it at that speed, which is and obviously it's hundreds of times heavier.
Yeah. In fact, that brings us on to a question here about, does the system add any additional weight to the train or perhaps reduce the overall weight? And there's a second sort of part of the question. Has Network Rail brought into hydrogen trains, or are they not so interested?
Regards the mass of the train, for the prototype, I think it slightly, I can't remember, I think it was a slight increase in the mass of the train, but this is primarily because we took all the seats out of that carriage and all of the interior fixings and replaced it all with the hydrogen and the battery. On a standard unit, you would see an increase.
Yeah, so the fuel cell itself, I think, was about 250 kilos, and then the tank system would have been 450 kilos or thereabouts. The battery was quite heavy at 2.5 tons, or there.
Yeah, I think all up it was 2.5 tons with its frame and everything.
Yeah, but it's an interesting question about the mass, because I know I mean, we're looking at like converting other rolling stock now within our group, and if you convert something like a locomotive and put the right energy and right power in it, and if you've removed a large diesel engine, normally you come up light. So we're looking at adding ballast to locomotives that would be converted to hydrogen because they won't be heavy enough.
Okay. You mentioned in your text, your next tests, you hope to reach 90 to 100 mile an hour. Do you see a future where this could be used for high-speed rail? In other words, are we going to have hydrogen on HS2? Or is it still going to be a pantograph?
No, the thinking, I think, on both of our Poprterbrook side and Birmingham side, is that electrification is the best solution for high-speed, high-intensity, high-performance running. So using hydrogen for the branch lines, where you can go up to 90 miles an hour to keep up with traffic on the main line, but then you can drive up onto a branch line and do the line speed there.
Okay. Can I just interrupt them? I've had several questions about where we can see a recording of this, just so people know. It is being recorded, and we have a YouTube site, and I will email everybody who's signed up to attend this talk with the YouTube link so they can sort of see it later on. Okay, technical one here. I understand the efficiency of electricity to hydrogen is up to 80%. There's also compression losses. Is this really the right answer? Where might improvements be made, as he thinks there might be some losses in the onboard electronics and electric motor? So in fact, you only get sort of a small amount of kilowatts going to the rails. In other words, what's the efficiency of the sort of system compared to, say, a diesel electric train?
Well, if you buy a kilowatt hour of electricity from the national grid and then use it to make hydrogen, and then do all the things you need to do with it, and then put it in a train, then put it through a fuel cell, and then get it to the wheels, then a lot of that kilowatt hours has been thrown away in the process. But it's which raises the obvious question of why not electrify. But I think that's the problem with the electrification, is there's the massive cost of like putting up the wires of several million per single track kilometre, which means that that becomes a big expense. So the way I think about it is we need to go to zero carbon electricity, which we are going towards, and then we can use that zero carbon electricity to make a mobile fuel that can be used to economically move a vehicle from one place to another. So I think we need to think about it in terms of economics, and yes, we want to get the efficiency of all those steps higher, which means that you'll need to use a smaller wind turbine ultimately and get a better system. So it doesn't really matter too much that there is an efficiency loss. Nevertheless, we want to get that minimized.
Okay. To give you extra hydrogen capacity, can you sort of mount tanks inside the carriages in areas such as like the Stadler 755 with its electric diesel trains, So in other words, would you get certification for that, or is storage of hydrogen still a major issue?
You could cannibalize one coach's passenger seating space. There's no reason why not. I think other than that, it's been covered.
Okay. Various designs for hydrogen trains have hydrogen stored in each carriage, which is more difficult for the UK's loading gauge. Could each train have a dedicated carriage for storing hydrogen?
Yeah, potentially. I mean, I think these are all really interesting kind of concepts, and you know, myself and Ross have looked at loads of different options. Everything's got a plus point and some challenges. Usually you normally want your hydrogen to be quite close to where your fuel cell is, because that limits the number of pipes and so on, and the distance that you're transporting the hydrogen. And you wouldn't necessarily want to transport hydrogen across between two adjacent vehicles on a train. So there's a huge amount to consider here, you know, we've looked at that, and there are lots of challenges, but we think they can be overcome and can make a viable product that people will use.
Okay. Do you think hydrogen trains are a transition or a permanent way for decarbonisation? And also, could you use hydrogen on freight trains, you know, much heavier trains than the passenger trains you're talking about?
I think it's here to stay. I mean, there's you know, the rail industry is a fairly small problem in terms of decarbonisation, as I mentioned earlier. I mean, the big challenge is kind of decarbonising things like heavy goods vehicles and buses. The road network can be achieved a lot with electric cars, can do a long way from that, but things like heavy goods vehicles, you can't really do that with a battery. And I think those sectors will probably end up driving the hydrogen economy more so than rail. So I think it will happen anyway. And if there could then be a really large market, a large amount of hydrogen produced for those markets, and rail then can just take advantage of that availability of bulk hydrogen at low costs. Okay.
There's a question here about driving technique. Do the driver's driving technique have any impact on the sort of the amount of hydrogen you're using? See, Ross is smiling, so presumably it does.
Yes, yeah. The driving technique is that there is a big impact on not just hydrogen usage, but diesel usage and the usage of electricity from the overhead. So yeah, driving style does matter quite a lot.
Okay. What are the planned development timescales on HydroFLEX 2? In other words, when do you see that sort of coming out for testing?
I don't know if I can actually say. If I can answer, I'll answer it on the website.
Okay. I was surprised at the 10 to 15 minutes refueling time to load 5 kilograms of hydrogen. What limits the speed of this operation? Is it cooling effects of decompressing the gas?
I think this one's for you, Stuart.
Yeah. Well, interestingly, hydrogen does a weird thing when you decant it from high pressure to lower pressure. Actually, it gets warmer. It's got a negative Joule-Thomson coefficient. So what happens when we decant it into the tanks inside the train, those tanks will actually get warmer, and the gas inside of there is hotter than the ambient. So we need to monitor the temperature of the tanks, and you end up overfilling the tanks inside the train, and then later on the gas will cool down and stabilize at 350 bar. So it's kind of a size of your pipe issue of what we're refueling it with, and also what temperature we allow the tank, the gas to get up to when we would put it in there. So if you put the hydrogen in there instantly, you need a massive pipe, and the gas would get really hot when it went into the tank, and you need to let it cool down later. But 15 minutes is sort of a target that we looked at to be comparable to what you'd need in a real life situation.
Okay. Our acceleration, Phil's come up, so I'll make this the last question. Are acceleration and deceleration compatible with existing trains, especially on branch lines where stations could be only a few minutes apart?
Yes. So even with the reduced power, even if you have a reduced power on a train like a 319, the initial acceleration is the same. It's just the speed at which that power sort of tails off is what changes. So if your stations were a few minutes apart, it wouldn't really be affected.
Okay. Well, I think much as we've still got a few questions, there's quite a few more. I'll hand you back to Phil. Thanks very much indeed, Ross and Stuart.
You're welcome.
Indeed, and it's a shame to interrupt you in full flow. You've both done a great job. Been an example of a good collaboration, I think, much like the HydroFLEX project tonight. And really interesting to see, what's going on in the HydroFLEX project, which looks to be part of the solution on the journey towards decarbonisation and meeting some of those UK targets that we have set. So once again, thank you very much, both of you, and I hope everybody else enjoyed your presentation as much as I did.
Thank you.
Thank you.
Thanks. So that brings us to the end of tonight's event, and that's the end of our normal season this year. We have a joint event with the Audio Society of Cambridge coming up in August. And we'll be back with our main programme for the 2021-22 season in October. And please remember, you can find out details of all events if you search or Google IET Cambridge Network, and you'll find our community website. Okay, so on behalf of the IET Cambridge, enjoy the summer, everyone, keep well, and you can all disconnect now. Thank you.